right. So, no matter what my initial investment's going to be, I want to double it. I'm going to divide by that 5,000, and that's always going to become 2. If this was 6,000, I want to double it. It's going to be a 12,000 on here, and that quotient's always going to be 2, right? So now, how do I address that t? How do I get that t out of the exponent? If I had 2 equals, let's just say, let's just do it this way. If 2 is equal to 3 to the x, how do I get that x out? How do I bring that down in front? Take logarithm, right? Okay. So is that what's going to happen here? To get this 2t out, take a logarithm. Okay. Does it matter what logarithm to take? No. Okay. So we'll take the natural log just because that's simplest. Take the natural log on the left-hand side, so it gives me ln of 2. I'll take the natural log on the right-hand side. So when you write this, maybe the first way you write it is I'm going to take the natural log, 0.05 over 2 of 2t. But now applying that rule brings that 2t out in front. And I'd be left with something like that. Does that make sense? Okay. Now, and it varies on how you want to kind of write this stuff. If you want to add that stuff together, you may do that, okay, and change that to just one value, ln of something instead of an ln of some. I'm going to leave it that way because a lot of times that 0.05 divided by 2, depending on how many times I'm compounding it, it might not be a real nice number when I sum it together. Right? I'm just going to leave it that way, okay? But ln of anything, as long as that's a positive number, is just a number, right? This is just a symbol for a number. Well, if I have 2 times that, isn't that just still a number? So isn't everything that's not, so everything over here that's red, isn't that just a coefficient for t? So let's divide both sides by that. If I divide both sides by that, on the left-hand side I'd have ln of 2 over 2 ln of 1 plus 0.05 over 2. And on the right-hand side, I'd have t. Have we isolated t? Yeah. So now, I'm going to start to grab Desmos. Desmos, like showing in front of you guys, isn't great because the solution, for some reason, they want it to be the smallest font you can possibly find. Okay, but I like the ability to type something in and it be in that kind of math print that I've written by hand, right? That's pretty easy to compare to make sure I've typed things in correctly. And you see there that we get all 14 years, correct? Okay. We can always check that. So I'm going to copy that value. If I type in 5,000, 1 plus 0.05 divided by 2, raised to the 2 times that number, what quantity do I end up with? 10,000, okay? So it does show me that I've got the right value there for time. Let's talk about continuously, okay? Now, it's the same amount of money being invested, same question about doubling, okay? But if I do something continuously, is that going to earn me money faster or slower? It's going to earn me money faster. So my years, in regards to the amount of years it takes to double, should be what compared to that 14? Should be smaller than 14, okay? Now, it's probably not going to be like 6 years or something like that, right? That's kind of crazy. But we're going to look at A of t. Now, continuously compounded was P e to the RT. That was that formula, okay? Now, like I said, your principal is 5,000 again, right? I want to double that, so it's 10,000 again, correct? Okay. Does that matter if that was 15,000 and asked me to double it? No. When I divide both sides by my principal here, when I'm trying to double, divide by p, it's going to go away, divide by p. Well, if this thing was supposed to be a doubling idea, that number right there should always be 2, right? And I'm left with then e to the RT. Now, all I know to be 0.05. Okay? Now, I said we'd come back and talk about this when we did compounding continuously. If I wanted to, we're doubling there. So doubling means that number on the left has got to be 2. If I was tripling, it would be a 3. If I was quadrupling, it would be a 4, right? What if I was halving it? What if I wanted to see how long does it take for me to lose $2,500? Okay? Wouldn't that be a 1/2 over there? Okay? So how does that compare to maybe something we've done in biology or chemistry? Or it's half-life. Okay? So we're talking about, basically when I see this type of situation, it's like a double life, okay, or a triple life. How do I increase that by 2 or 3 or 4 times? Well, if I want to half-life it, that 2 would be a 1/2. Okay, so those are things we're going to talk about here in a little bit. But I like to draw those kind of parallel comparisons so that you understand when we get to half-life, it's no different than anything we've already done. Okay. How do I get this t out of the exponent now? We'll take natural log both sides, right? Okay. Now, does it matter whether I take the natural log or not? No. The reason, though, we take the natural log is because when I take the ln of this, I take the ln of that, so the ln of this quantity, you bring that exponent out in front like we did here, and you're left with ln of e, right? What's ln of e? 1, okay? Or you think about it this way, well, if I took ln of e to the 0.05t, we've talked about this a lot, our property says that you can be left with just that expression because of this idea, okay? So ln of e is just 1, so basically I'm left with just 0.05t. So ln of 2 divided by 0.05 is going to equal t. And now, looking at that, don't like that. Ln of 2 divided by 0.05. And we see that we get about 13.86 years. Is that right? So sometimes the question is, well, what's the difference? How many years difference in regards to compounding semi-annually to compounding continuously? So can I just take that number there and subtract from it that number there? And I get that. Does that make sense? Okay. We talked about this a little bit in the last class. My question is, how many days is 0.172 years? It's about 63. Yeah. Okay. Now, so the way we do that, okay, I want to get to days. Okay. Well, you guys have done this in other science classes, hopefully. I know we did this in geometry towards the end of the year in geometry when you guys were 9th and 10th graders. But we did unit analysis, and that's what this is. I want to change years to days. Okay? Well, I need this because this is over 1, right? So this is a numerator. Years is a numerator. So when I multiply, we call it process unit analysis or dimensional analysis. We always use multiplication of conversion facts. Okay? So what I need to understand is that I need years to disappear. So the only way years can disappear is if they give me a quotient of 1 with their units, right? Okay, so I need a years up top in the numerator, and then I need a years on the bottom. Well, is there a direct link between years and what I want to get to, days? Yeah, you know that conversion fact, right? So what do I have to do here? Years, what numbers do I put in here? 1 and 365, right? Okay. Now, we could obviously, because 365 to 1 year is not exact, right? Okay, because a leap year and all that kind of stuff. But we want to get more precise, we can get more precise with that number. What if I didn't want to get to days, but I wanted to get to hours? Yeah, then I would multiply and say, okay, well, days to hours. I want to do this real quick, because I want to see how many years this would be, because this is something we're going to have to do. Sorry, how many days this is. This is something that we're going to be asked to do in trig, and I think we'll get a jump start on it right now. It's going to be pretty beneficial. So I'm going to take that number, 0.17, and multiply it by 365. And it gives me 62.989 days, right? Well, I want a more accurate time than just days. Okay, so that means to so the difference, I guess, between these two procedures is 62.989 days, which is into the 63rd day, right? Okay, but how far into the 63rd day is my question. So can I take this number here, and this is the approach that we do, or we use. Can I take that number, subtract 62, and that then is the portion of the 63rd day? Okay, well, what happens if I want to go from days, so I got 0.989 days, and I want to change that into hours? What would I multiply that by? Yeah, multiply that number by, I don't know why it keeps putting those brackets there. Multiply that by 24. So it gives me 23 hours. Okay, so it's 62 days, 23 hours. Let's take that number. Subtract 23 from it. Take that number. Let's say I multiply it by minutes. How many minutes? 60. So right now it's 44 minutes. Can I keep doing this? So I think maybe the easier thing is just to delete the 44. So we always subtract that whole part, because that tells me then the portion of the 45th minute. So multiply that by 60, and it gives me 42 seconds. So right now I know that I'm dealing with a difference in these two procedures of 62 days, 23 hours, 44 minutes, and 42 seconds. Okay? And that's something that eventually when we start in trigonometry, they're going to ask us to do, because we're starting talking about degrees of angles, and something that you guys talk about degrees of angle. I could say like 43.5 degrees is an angle, right? Well, we like to talk about that a different way in trig. We like to talk about it as 43 degrees and then 30 minutes. Okay? So a degree is broken up into, so a circle is broken up into 360 degrees, right? Each degree is broken up into 60 minutes, and each minute is broken up into 60 seconds. Okay? So those are things that we'll talk about, and we can thank the Babylonians for that, because they had a base of 60, and it just gets messy. But if you were to go to like Google Maps or something like that, and you look at longitude and latitude, they're in degrees, minutes, seconds. So those are things we'll talk about. Now, getting back to this logarithm exponential stuff, when we talked about A of t is equal to P-E-R-T, P times E raised to the RT, obviously R was an interest rate, right? But it's a rate of growth, correct? Okay, if it was positive. T was a time. P was your initial amount. P was an initial investment. A of t is then an amount after some time. That is exponential growth. Anything of that form is exponential growth. So, a lot of times you might see this formula, and we're using different variables, but is A sub 0 a way of saying this is the amount at time 0? If I'm talking about dollars, that's my principal, right? Okay. Another way you might see this, and I'm not 100% sure on what the purpose of the n is. Do a little research and see why they use this. but I see that formula a lot, okay? But P, A sub 0, N sub 0, they're all my initial amounts. Does that make sense? A sub T, A of T, and N sub T, those are just my amounts after a certain time has elapsed, right? Okay? Every single thing that goes through exponential growth is of that form, okay? We call that our exponential growth model. Because the idea, and how's that different than what we've talked about with compounding like annually or semi-annually or monthly? When we're doing something that's continuously growing, like bacteria or infected people in a population or whatever, something that's continuously dividing itself like cells so that their population is increasing all the time, okay, is that every single instant is a new time period which we have more of what we are of our object than what we had in the last time period. Does that make sense? When bacteria and cells and other things and just viruses spread or whatever in a population, they don't wait a month to double right away after that month elapses. Does that make sense? And then we start with like 10 things, kind of like maybe I start with $10 in a compounded monthly investment. Start with $10 and only have $10 in my hands or in my account for 30 days. You know, on the 31st day, now it goes to $15. And now all I have is $15 in my account for the next 30 days. And then right away, then on the 31st day, I now have $17.5. Does that make sense? Okay? It's continuously growing when we talk about the spread of bacteria, the spread of viruses in a population, that type of stuff. Okay? So every single instant, that is getting bigger and bigger and bigger and bigger. Okay? So that's the idea of why these formulas are kind of all the same. Now, the reason I bring this one in is because that's one you see a lot of times with half-life. Okay? Now my question, and I'm going to go to a different slide here real quick. It might be just a different PowerPoint. Yeah. When we are looking at N of T is equal to N sub 0 E to the RT, and we're talking about growth, okay, that's an exponential function. And that exponential function is going to look like that, right? Okay. Now the idea is that this is T, and this would be N of T. This would be the amount after some time, right? So a lot of time with exponential growth, we're looking at times being positive, right? So a lot of times we're not looking at this garbage over here. How do I get, though, if that's growth, as time gets larger and larger, what does decay look like as time gets larger and larger? It would look like that, wouldn't it? As time goes to the right, we're getting smaller and smaller y values or N of T values, or N sub T values. How do I get, with this equation here, how do I get that transformation? How do I get that point there to come essentially over here? That point there, cursor died. All right. How do I get that point there to come there? This point to stay, this one to come over here, that one to come over here, so that when I do trace that out, I get this curve right here. How do I do that with transformations? A reflection. A reflection over what axis? The y-axis. When I reflect over the y-axis, okay, where do I negate? Where do I multiply by a negative? Do I do it to the whole thing? Do I put a negative out here in front of the whole thing? I do it to, ultimately, if it was the x and y axis, it would be to the x, right? Okay. but now my x-axis is a t, right? Okay, so I'm going to do it to the t, just kind of follow my line of thought here. I'm going to do it to the t. So I do something like that, right? Okay, that would get me the kind of the graphical reflection. But is that negative? Can that be brought out here instead with the r? Now the reason I want to do that is time. We should have the idea that time is always what? Positive. Okay. And the way we, basically we're looking at elapsed time, so it's going to be a positive amount. So we let the r carry the negative in that case. Okay. So that would be your growth model for decay. Now a lot of times we just use that blue one. We say n of t is equal to n sub 0 e to the rt, and that is the model that represents growth and decay. But if it's growth, r will be what kind of number? Your rate would be positive, right? If it's decay, your rate is going to be negative, right? Okay, so I want to do a question here, and we might actually get through maybe a couple questions that the last class didn't have the opportunity to see. Do this one. I want to do this one because it's very similar to what you're going to see next week, and it's going to be very similar to what you see on the 10th and 11th and the 9th, whenever we take that final, whatever those actual dates are. But it says a bacteria culture has an initial population of 6 billion. Okay? An initial population of 6 billion. So right there, initial, okay, this 6 billion is going to be my n sub 0, right? Does that make sense? So an antibiotic is applied and causes the bacteria to decrease. Decrease, right? So we're talking about decay. So the half-life of the bacteria is 7 hours. How many bacteria are left after 9 hours? Okay. Here's the thing. We're going to go n of t is equal to n sub 0 e to the rt. We're talking about decrease. So r has to be what? Yeah, r needs to be negative. Now, I'm not going to put a negative in there because we have nowhere in here does it tell me my rate of decrease, right? Nowhere does it tell me r. So I'm going to actually have to find that. And when I find it, I'm going to evaluate it and see if it becomes a negative number just the way it's presented, okay? If it is, then awesome. I just plug that in as r because it's already negative. I do not want to put a negative in my formula because if that r is negative when I evaluate and find it, and then I have a negative in my formula, doesn't that negative negate a negative and make it positive? And now I'd have a growth rate, and that's not what I want. I want a decrease. But they do not tell me my rate of decay. Okay, so if I were to go start filling things in based off of what we know here, okay, it's asking me if I start with $6 billion, or 6 billion bacteria, not dollars, bacteria. E is always E. Obviously, we said our interest rate, and I get money in my mind. My rate of growth or decay is R. I don't know that. Okay? It wants to know how many bacteria you're left with after how many hours? After 9 hours, right? Now, my question is, how many variables do you have left over right there in that equation? You have two. You have R and you have N sub T, right? Our goal is to solve for N sub T. That's what we want. Okay? So we got to find R. And all the other information that they provided us, and numerically it's only this number right here, is going to allow us to find R. Okay? But we're going to use the exact same principle, the exact same formula. N of T is equal to N sub 0 E to the R, but with half-life, my T is going to be the number of hours it takes to get half-life, right? Does that make sense? Now, this is the reason I introduced with that compound continuously question beginning with the 5,000 and the 10,000 question. Here, I don't know what that number is, and I don't know what that number is. But that's an initial amount. this is the amount after my half-life elapses, right? By definition, half-life says if you start off with 100 right here, then you'll get 50 here after that time elapses, right? If you start off with 700 here, then you will be left with 350 here after that time elapses, correct? And both these are going to have the e to the r times 7 on them. What would you do with either of these to isolate that exponential part? You divide by that 100 or divide by that 700, right? And when I do that, what's that always going to give me on the left-hand side? A half. So you get 1/2 equals e to the 7r. Can I now use logarithms? Take the log on the left-hand side. Take the log of the right-hand side. So when I do that, that 7r can come out front. And I'll be left with ln of e, right? What's ln of e? 1. Okay, divide by 7 then. Ln of 1/2 over 7 is equal to r. So right now we have our value of r. If you were to evaluate that, you're going to see that when I take ln of 1/2, I believe it gives you like negative 0.69 or something like that. Divide that by 7, it's going to be negative, right? So r becomes negative. What I want you guys to understand is ln of 1/2. No matter what I start with here, if I'm doing a half-life, that is always going to be a 1/2, right? No matter what. If I was doing, a quarter life, that would be a 1/4, right? If I was doing that doubling idea, that'd be 2. So when I'm doing half-life, my r value is always ln of 1/2 divided by, what was that, 7? 7 was the half-life, right? All right, so if you take, you're going through a question, and it's a half-life question, and they do not give you the rate of decay. It is, if you don't want to go through that blue process that we went through, you can always take ln of 1/2 and divide it by whatever your half-life was, and that's going to give you the rate of decay that you need. Okay? So now, if I look at the overall question, it says, what is n of t? If I have 6 billion, I apply 6 billion bacteria, I apply this antibiotic, okay, and I have now r to be that number. Ln is be kind of messy here writing this in. Ln of 0.5 over 7 times 9 then, okay. Is this my only variable left over then? All right, so let's type this in and see what we come up with. So we're going to 6e raised to the, I'm sure like 9, is it okay to go with 9 ln of 0.5 all over then 7? And you see there it's a 2.46 number back, which is 2.46 billion, right? Now let's think about this. If I were to do the half-life idea, okay, so let's say, I just want to create a chart. I figured out the best way to create this chart. Started with 6 billion, right? So after one half-life, so this is my half-life, this is my quantity. After one half-life, what would I be with? 3 billion, right? Okay. After a second half-life, what would you be left with? 1.5. After a third half-life, what would you be left with? 0.75, right? Okay. Now think about this. One half-life, they said our half-life is 7 hours, right? This would be 14 hours. This would be 21 hours, right? How many hours elapsed throughout this procedure? 9, right? So wouldn't 9 hours be somewhere in between those two? And 9 is closer to 7 than it is to 14, right? So does it make sense that my answer of 2.46 is pretty close to 3? So those are little things that you can maybe go through when you get an answer, and maybe you're not confident, but you can kind of think, okay, I understand if a half-life idea just means I'm cutting my quantity in half every kind of iteration of half-life, okay, of those hours, and we can kind of argue that our answer does indeed make sense, okay? If we've gotten like 0.46, maybe that doesn't make a whole lot of sense. Or, you know, if I mess something up and I get a number like 8 billion, is that a problem? Yeah, because I grew, right? But those are things that, you know, scientists, pharmacists, they're interested in. Think about, now we talk about half-life here, about a bacteria, but when you take a medicine, is there a medicine rate of decay when it enters your body? Yeah, and it wears off, right? So pharmacists and labs will be interested in being able to do that and understanding how that kind of dynamic works with that particular type of medicine. We got time for one more. Let's this one here, okay? Put a star on that. Okay? Something that you're going to want to be able to do. Huh? I'm not going to give you that exact problem, but I'll give you something similar to it. All right, so this is another one. That is, we actually have to do a little preliminary work here to address this, but this is a common type of thing to do with population growth, okay? Whether it's people, bacteria, whatever. You know, it might be interesting, like some bacteria in some like petri dish or something like that growing, and we measure 2 time periods. But here it says 1970. The U.S. population was 203.3 million, okay? And I think I recall, I think I took this from a stats book, so I think this is true. 1970, we had 203.3 million. By 2010, it had grown to 308.7 million. By what year will the population reach 335 million? So this is, population growth is always exponential, okay? So, you know, you maybe at one point would have done something like this. In 1970, we had 203.3. In 2010, we had 308.7. And you use those ordered pairs, and maybe you even did this. You said 1970 was year 0, and 2010 was year 40. Does that make a little bit more sense? Okay. And maybe you use it, they said, oh, this data, this growth is linear in nature. And then you can create an equation of a line, right? But now we know population growth is not linear, it's exponential, okay? So they ask us, can you project when there's going to be 335 million? I don't know my growth rate, right? When I think about my formulas, A of T is equal to A sub 0 E to the RT, and whatever variables you want to use, A, P, N, whatever. We now have some information here to actually allow us to find our rate, okay? What was my initial amount? 203.3. Can I go 203.3 right there? E, R, I don't know. That's what we're looking for. We're looking for a growth rate. Okay? And we know it's a growth rate because it's increasing, right? If it was decreasing, the growth rate would be negative. It would be kind of like that half-life problem. Okay? But T, do I know T? T is the difference in these 2 years, right? So the time elapsed was 40 years. What is A of T then? It's what I'm left with after that time elapsed, 308.7. So now, if I divide by 203.3, okay, so I'm just going to 308.7 divided by 203.3. All right, so this gives me, I'm going to write it this way, I guess, because I want a more accurate answer. So I get something like that, right? But 308.7 over 203.3 is 1.518, okay? So instead of asking maybe like a half-life question, this is more, or a doubling question, this is like, you know, what is the time that it takes to take this population and let it increase by half? Does that make sense? Okay? Or 3 halves concept, multiplying by 1.5 there. Can I solve for R by taking the natural log of both sides? Okay, so I'll take the natural log of 308.7 over 203.3 is equal to 40 R ln of E, right? What's ln of E? 1 divided by 40, right? Okay. That should give me R. Now, what you would see maybe sometimes, and we talked about this in the first class, sometimes in WebAssign, if you mess something up, if they ask for like R here, and you type it in this way, and it was wrong, their feedback might be something like this. Does that make sense? Can they do that? Yeah, those two things are the same because when we have division in our argument, we know we can expand that into subtraction, right? So knowing those different properties might allow you to analyze that feedback a little bit in WebAssign. All right, so that's just R. Let's calculate what that is real quick because it's going to getting messy if I just leave those as the exact values. So I have ln of 308, fingers don't want to work, divided by 203.3. I'm going to divide that by 40. So there is my R value, right? Okay. So now the question is, if that's R, let's go back to A of T is equal to A sub 0 E to the RT. Now they want to know when will this reach 335, right? When will it reach 335? Well, what was my initial amount again? 203.3. I know E is E always. R now is this 0.010 number, right? Times T. Can I now use logarithms again to solve for T there? All right, so just kind of quickly doing that. We would divide both sides by 203.3, right? Left with E to the 0.010t. Can I take natural log both sides? Natural log of both sides would be 335 over 203.3. It's going to leave you with 0.010t, right? Now what do? Divide both sides by that, right? And that's going to give me t. So what I'm going to do is I'm going to take ln of 335 divided by 203.3, and I'm going to divide that by, I'm trying to recall this number here, Control C, Control V, divide by that, and it gives me T to be 47 years. Okay? Well, the question was when. It didn't say 47 years as the answer. It didn't say how many years. It said when. So my initial time was when? What year? 1970. So I take 1970, and add to it that number there, right? So it's going to give me 2017.829. Okay. Now, would that 0.829 allow me to talk about how many months that would be, and what month it would be, and on what day it would be? And I could kind of figure out then what second eventually it would be that we get to exactly 335 million people, right? Okay. Now, there are models that kind of impact population growth. Okay, we call them logistical models, where like, let's say we're talking about population of rabbits. Well, aren't there populations of other animals that might impact that population of rabbits? Okay, so eventually we talk about in a calculus course, like a third or fourth year calculus called differential equations. You start talking about how other populations impact current populations, okay? So this can get a whole lot kind of more precise based on other kind of confounding variables maybe. But hopefully that at least gives you somewhat of a little bit of insight on real life applications of some of the math that we've been using. Tomorrow my hope is to go on to sequence as a series. Knock those out by maybe Tuesday of next week. And then maybe prepare wrapping loose ends up on Wednesday, test on Thursday. And then be sad on Friday. The last day you see me for 16 days. That would be pretty saddening, I would think.
What am I going to do? I don't know. All of you sweet boys.
There you go. There you go.